Lesson 3.5, Symmetry. This is one of those lessons that's kind of fun for people that are visual people because there's not a lot of calculations or math. There's just a lot of visualization of what we're going to do. But for other kids, it's going to be really hard because you do have to visualize and you can't actually see it. So it's going to be hard a little bit. So let's pay attention. And if you've been in an art class, a lot of these things that we go over today might be familiar. It says, look at the kaleidoscope image shown. Then consider piece A and B taken from the image. So they just cut out this image and from this original visual. How are piece A and B related? So visually, how are they similar? And maybe how are they composed? How did they were created? And then you're going to describe a sequence of rigid motions, what we just talked about, rotation, reflection, and translation in the previous videos. How many rigid motions do you need to produce the entire image from piece A? So look at this carefully, look at the entire image, compare these two, and then figure out how many of piece A's do you need to create that entire image. Example 1, identifying transformations. So a couple different types of transformations for symmetry. So symmetry, what transformation can be mapped? Mapping the figure onto itself. So think of mapping as taking something and putting it right back on top of itself where you can't even see it. So if I mapped my hand, it's obvious that something changed. But if I mapped my hand, rotated the whole thing around and ended up just right back here, you would not even notice that it changed. Well, some things you can reflect and you won't notice the change. Some things you can rotate and you wouldn't notice the change. So that's what we're going to talk about. So this one, it's going to talk about symmetry or a rigid motion onto itself, and it gives examples of reflectional symmetry. This is one of those vocabs you need to know. So reflection, symmetry, if I put a mirror right here and reflected this over the other line, it would be like nothing happened. You can't even see it. It's the reflection of itself, and it results in the original figure. Or you could result this way. Here's the mirror or line of reflection. It's that perfectly horizontal. Keep in mind that lines of reflection do not have to be perfectly horizontal and vertical. Okay, so these are the reflections or the lines of symmetry that would create this, mapping it onto itself. There is also a rotational. So reflectional symmetry, rotational symmetry. This is when you rotate the image and it maps onto itself, kind of like my hand. But my hand, you had to rotate all the way 360. That we don't count that as rotational symmetry because everything that rotates in a 360 degree would end up on its own, and mapped onto itself. So we don't use it. It's between that, or anything less than 360. So anything less than 360 degrees and maps onto itself is considered rotational symmetry. So rotating 180 around point P will map this original figure onto itself. Transformation for this. So think, does it have reflectional symmetry? Does it have rotational symmetry? Make sure to check your answers to see if you're on the right track. And here's another one. Does it have rotational? Does it have reflection, line of symmetry for this figure? And here you have to identify how many lines of symmetry would a hexagon have. Now, to be honest, lots of kids, when they're given a question like this, how many lines of symmetry or how much of rotational symmetry is in a figure, they draw it out. So I would draw it out for sure. So here's an example. Here's a hexagon. So opposite vertices. You have to know what vertices are. Vertices, or a vertex, that's the point right here and here. So opposite vertices, it's basically taking a mirror from opposite corner to corner. Okay, those have locations, 3 different locations for reflectional symmetry. Or opposite sides. Look here, it's not intersecting the corners, it's intersecting the sides. So there's 3 more possibilities for symmetry. So the bottom line is a regular hexagon has 6 lines of symmetry. drawing it out, you can really see the difference. How many lines of symmetry does this figure have, and how do you know? Make sure to check the answer. Here's another one. How many lines of symmetry does this have? Okay, be careful, double check. Check those answers, make sure you're on the right track before you move on. Now we're going to talk about rotational symmetry. This is where some math is involved. Not a lot of math, but there is math involved. For what angles, so this is actual angles, talking degrees, of rotation does the figure map onto itself? This is an equilateral triangle. It tells you that. And then it gives you a tool down here. This little tool. Now if I move this, watch the visual. If I rotate, A prime is going to land up right on C. Hopefully I can get it perfect. I went a little too far. You get the idea. My hands are not, there it is. So there's one rotation, one rotational symmetry, and I'm going to go a little bit further to point B, trying to line it up. There. There's another one at 240, and then I'm going to go all the way back, and then I'm back at the beginning where I started from A to A prime, but that's 360 degrees, and we don't count that 360. So look at this solution. It says it rotates to 120, way back here. There's 120 degrees-ish when I get there. And then rotate it again to 240, but then we don't count the 360. Okay, so it has two different degrees of rotational symmetry. Another one, you can rotate this down here. Rotate, rotate, still not mapped onto itself. Hopefully you can see it. It's supposed to be 180 in my hands. I don't know if it's just me. Maybe you guys will be better. There it is, 180. Then I rotate all the way again, 360, but we don't count that 360. So the solution, it has rotational symmetry of 180. When it's only 180, like 180 degrees, okay, not 360, but 180, and you rotate it 180 degrees, there's another name for it. It's also called point symmetry. Some textbooks use this, some don't. So basically, rotating at 180, just 180, is also called point symmetry. Go ahead and try this one. So how many times can I rotate this point? Little hint for you. And you can visualize it. You can, if you have a hard time with this, trace the paper or the figure with paper and physically rotate. How much are you rotating each time? How many degrees? And then this one. Again, feel free to use a Post-it note or paper, trace the figure, and physically rotate it. Now you have to determine the symmetries. I love this problem because not only does this figure have reflectional or lines of symmetry, so if I cut a line or reflection mirror right there, it would be the same on both sides. So that's definitely reflectional or reflective symmetry. But I could do one here, I could do one here. So there's going to be multiple lines of symmetry, and there's multiple rotational symmetry. If I take the top of this petal right here and rotate it here, 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 each time I rotate it, it would look identical. So look at this solution. First, they visualize it for you. They draw in the lines of symmetry. Then they talk about the rotational symmetry, which shows you how to do the calculations. So we know there's 360 degrees from the beginning all the way around to where it started, from where it started. So if I know this petal can go 1, 2, 3, 4, and end up here at 5 again, then I basically take 360 divided by those 5 movements, okay, and you get 72. So that means from here to here would be 72 degrees, and then add 72 more. And so that's how they get the 144, and then add 72 more, that's 216. Add 72 again, that's 288. And if you added 72 one more time, you'd be at 360. But again, we don't count 360. Try this one. Types of symmetry, rotational and reflection. Is there a line of symmetry, multiple lines? Are there rotational symmetries, multiple different degrees? Try to figure that one out. And then what symmetries do or does a square have? So you might want to draw it. You might want to physically draw in some lines. and physically rotate if you need to visualize a little bit better. You are going to be using symmetry. So here's like an application. A CEO of a company wants a new logo that looks the same for each rotation of 30 degrees. So 30 degrees, 30 degrees, 30 degrees. Every 30 degree, it looks identical, which means it maps onto itself every time 30 degrees, all the way around to 360. So what are some possible logos, designs? There are so many answers for this, but the solution actually gives a visual that is pretty cool, and you can go through the steps with that if you would like. Here you're going to actually try it. What is a possible design for a circular logo that looks the same for each 60-degree rotation and uses at least 2 colors? So this one requires a lot more time. Talk to your teacher and see if they want you to actually design that, but it's kind of fun to work with these tools and see if you can actually design something. Okay, overall, this whole lesson 3.5, is about symmetry, reflectional symmetry, rotation. So if you can draw a line through the figure and it's a perfect mirror image of itself and it looks like nothing even happened, then it has reflectional symmetry. If you can rotate a figure and it is mapped onto itself, then it has rotational symmetry, and you have to figure out the degrees. So how many times 360 degrees divided by how many times you can rotate it and still end up on itself. I hope that helps.